Good day, everybody, and welcome to this special session on the Biobank Virtual Scientific Conference. The importance of the environment in interacting with our genetic makeup has become all too apparent with the fantastic phenotyping and genetic studies that have been undertaken on the UK Biobank. And I think today we're going to be looking at how different environmental exposures can interact with the complexity of our genetic makeup in a number of different ways. But I think it's the use of this biobank as a national cohort, in which there has been detailed phenotyping, which has been very carefully controlled over the repeated measures that have been made and enriched within the last few years by imaging and other useful diagnostic interactions. We've got a fantastic lineup for this afternoon's discussion and panel meeting, and the way we're going to run this is to have 4 10-minute talks which will follow sequentially, and then we'll have a 20-minute period for discussion. And please do send any questions you have to the chat box so that we can have a look at those and select them for the 20-minute period at the end. But without further ado, I'd like to get straight into the session by introducing our first guest speaker, who's Dale Sandler, Senior Investigator and Chief of the Epidemiology Branch in the Intramural Research Program at the National Institute of Environmental Health Sciences at the NIH in the United States, where she leads the Chronic Disease Epidemiology Group. And Dale is going to tell us about leveraging cohorts to study the impact of environmental exposures on health. So over to you, please, Dale.
Hey, well, thank you for inviting me to speak today about leveraging cohorts to study environmental health. Environmental exposures can affect health at many different stages across the life course, and the increased interest in using cohorts to study the environment may be driven in part by the increasing availability of measurement tools, as well as concern about the impacts of climate change. Environmental exposures can be broadly defined, including a whole host of exogenous exposures, as well as several endogenous measures. Potential sources of environmental exposure data in cohorts includes questionnaires and biological samples, but until recently, few cohorts have used these resources to study ambient non-lifestyle environmental exposures. A surprising source of environmental data is epigenetics. We know that the environmental and lifestyle exposures can affect epigenetic mechanisms, and there's been some recent success in defining epigenetic signatures for specific environmental exposures, such as cigarette smoking. So I'll skip that. So finally, the rapidly expanding availability of personal monitoring devices, applications linked to smartphones, and increasing availability of geospatial data collected for other purposes that can be linked to cohorts is greatly increasing the possibilities for studying effects of environmental exposures. As exciting as this is, there are still some key challenges, including variability in monitored exposure data over time and space, the fact that the developers of modeled exposure indices frequently update and improve their indices, and so exposure information is not comparable over time, and the fact that outdoor exposures may not actually represent the biologically relevant exposures. Finally, the massive amounts of data that can be collected using continuous monitoring presents both bioinformatic and ethical challenges, such that the people who the people who actually agree to be biomonitored might not be representative. So because data are widely available, that doesn't mean that they are always appropriate. And one of the most frequently encountered challenges is the question of whether or not the timing is right. Data are collected but for other purposes are collected, may not be collected at the time that's most biologically relevant or at the for other questions include is the spatial coverage right, and the resolution of the data, as well as how variable exposures are over time. So despite these challenges, we've started to use a wide array of environmental exposure data sources to study health effects in the cohorts that I lead. And I wanted to share some examples from two cohorts. The first is the Gulf long-term follow-up study. This is a study that actually was designed to measure an environmental exposure, health effects following the Deepwater Horizon oil spill. Oil spill exposures were measured at the outset and linked to health effects, and we found a wide range of health effects that were associated with cleanup work. But these effects were much stronger than we had anticipated based on the relatively low levels and short-term nature of the exposures that people encountered during cleanup. So which led us to ask what else could contribute to susceptibility and disease risk in this cohort. The cohort is medically and socioeconomically disadvantaged, living along in the Gulf Coast region. They're at high risk for natural disasters. They've experienced multiple hurricanes prior to and since enrollment. And the Gulf region is home to some of the top emissions producing plants in the United States, and it's long had the reputation as Cancer Alley. So to address the first possibility, we considered a measure called, neighborhood disadvantage using an index called the Area Deprivation Index. That's a census-based measure that can be linked to residences at the census block group level. The Area Deprivation Index percentiles are available for the entire United States, and using the 2010 version of the index, which coincides with the enrollment of our cohort, we assigned percentiles to the residences of our study participants. So as you can see in the right-hand slide, the neighborhoods where our participants live are among the most disadvantaged in the United States. We found that a number of health effects that have also been associated with oil spill exposures were associated with neighborhood disadvantage using the Area Deprivation Index, including decreased lung function and increased epigenetic age using a methylation-based measure of methylation-based mortality predictor known as GRIM-Age. In considering widespread chemical exposures in the area, we first found that blood levels of styrene, a known neurotoxin, but not an oil spill chemical, were higher in a sample of study participants than in the US as a whole. Using modeled air toxics data from the US EPA, we then found that increasing quartiles of ambient styrene exposure were associated with increased reporting of clusters of nervous system symptoms. Can't use my computer. We also found that those same symptoms were associated with increasing levels of particulate matter air pollution. Lastly, mental health effects are commonly seen after major disasters, and the Deepwater Horizon oil spill was no exception. Anxiety, depression, and PTSD were assessed with standardized scales and were associated with most cleanup exposures. But as shown here, poor mental health outcomes were also impacted by having also suffered losses from Hurricane Katrina 5 years before the oil spill, such that those who experienced both oil spill work and hurricane losses had higher prevalence of these mental health outcomes than those who had just one or none of the exposures. So to consider this further, we've started using something known as SHIELDAS, the Spatial Hazards and Events Losses Database, that compiles data from FEMA on hazard events in the United States. It goes back to 1960. We summarized data from 2005 to 2010 and created multiple summary measures And we were able to show that PTSD was associated with many of the indices reflecting serious losses that we created. So since the Gulf study was actually an environmental exposure cohort, I wanted to give some examples from my sister study cohort, which, although it was designed in the 2000s to study environmental risk factors for breast cancers, it was started before their advances in technology and geospatial databases allowed us to do anything remarkable in terms of assessing environmental exposures. Instead, we relied heavily on questionnaires and individual biomarkers. We're now linking the cohort to cohort enrollment and subsequent addresses to neighborhood measures of socioeconomic status and environmental exposure. And we've been adding new omics technologies. The sister study, like many volunteer cohorts, is better off than the US as a whole, and few live in high disadvantaged neighborhoods. But even so, we've shown that even in this cohort, increasing levels of the area deprivation index were associated with worse health outcomes, such as hypertension risk and epigenetic age, as shown here. We recently reported associations between criteria air pollutants and breast cancer that varied substantially across regions of the United States, potentially due to differences in particulate matter chemical composition, as well as exposure sources. And we've also been using multiple methods, different methods to assess traffic-related air pollutant exposure. For example, we've used the National Air Toxics data to measure, to assess census tract level exposure to diesel particulate matter and PAHs. We've used measured distance from roadways, and as well as self-reported data on observed traffic intensity at study enrollment addresses. In a current study of olfactory impairment, which increases with age and is common in many neurodegenerative diseases like Alzheimer's disease and Parkinson's disease, we found that diesel exposure levels in the 95th percentile only were associated with olfactory impairment, as was residential proximity to interstate highways and self-reported traffic intensity. So in terms of next steps for our cohort and other cohorts, we're planning to add many novel exposure indices that we can link to various residences reported by study participants, including additional measures of social vulnerability and community resilience, redlining, proximity to industrial emission sources such as dioxin, daylight, light at night, flood risk, and wildfires and heat, which are currently of interest in terms of climate change. We want to account for exposure variability of time. Over time, we need to characterize early life exposures. And we intend to use other measures to validate some of these GIS-linked data. Finally, we think it's very important that we and other cohorts consider multiple simultaneous exposures before moving beyond the one single exposure at a time. So, thank you.
Thank you very much indeed, Dale. You've given us a wonderful introduction with a wide range of exciting and important studies collecting, obviously, these environmental insults to adverse health effects across the life course. And obviously, there are challenges in all of this, and maybe we can visit some of those as we get into the panel discussion a little later. So thank you very much. And now I'd like to introduce Dr. Antonio Gasparini, who is a professor of biostatistics and epidemiology at the London School of Hygiene and Tropical Medicine. His interests encompass various research areas in epidemiology and public health evaluations, from methodology, applied research, and software implementation. Professor Gasparini is going to give us a talk now linking environmental exposures to the UK Biobank, current activities, and future plans.
Okay, thank you, Stephen, and thanks to the organizer for giving me the opportunity to present today. So I would like to give you a couple of perspectives today. One is the perspective of the epidemiologist using the UK Biobank for doing epidemiological analysis on the health effects of environmental exposures. The other one is a researcher engaged in complementing the data in the UK Biobank with some measurements of environmental exposure. So I'll start very simply showing to you that there are many types of environmental stressors that we can look at. For some of them, for example, air pollution, we have established, let's say, evidence. Others are newer, for example, extreme temperature, very interesting nowadays because especially of climate change, but for which the evidence is existing, but probably coming mostly from administrative and aggregated level analysis. Others, for example, pollen, or it has been mentioned, noise. Of course, there's evidence in the literature, but of course, they are less studied than others. Now, when we come to study this kind of environmental stressors, we face traditional limitations as epidemiologists. The main problem here is that the risks are usually very small, but they apply to the whole population, so the impact is noticeable. But at the same time, we need to run very large studies. And we encounter a few problems. First of all, we need to study entire population and assign environmental exposure to everybody. We usually relied in the past mostly to monitoring data that, of course, are limited to few part of the population. For example, mostly on urban environments, for example, for air pollution. And especially, there is a big error in assigning these exposures. The other problem is that we rely often on administrative data with lack, let's say, of information on many individual level information. So the Biobank provides two opportunities. First of all, we can now exploit new data resources and technology, the modeling technologies to assign exposure to a much, let's say, finer level, and especially through the linkage to the UK Biobank. Is it possible to link this information with a trove of data, wealth of data on potential effect modifier on susceptibility factors that will be impossible otherwise? So it's not an exaggeration to say that the UK Biobank can become one of the best database available for studying health effects of environmental exposures. Now, of course, there are already some data available in the UK Biobank, in particular on multiple air pollutants and noise pollution. Some studies have already been mentioned, but there are limitations on this data. First of all, they were linked some time ago, so especially they are available only for the period 2005-2010. They are only represent yearly averages, and they are derived from a Europe-wide land use regression models that, of course, they have limitations. So the potential improvements are to update this data to more recent years, provide temporary stratified data, being able to study, for example, not just long-term, but also short-term associations. And we can make use of novel and improved modeling techniques with higher precision. So recently I had a project approved with these specific objectives. One of them is to reconstruct individual level exposure histories for multiple environmental stressors. And second, to derive novel epidemiological designs and apply these methods to investigate accessibility profiles and risks varying at the individual level across the Biobank study. I will focus today, of course, on the first objective. We have just started this study, but of course, I look forward to present some results in the future about some analysis on the UK Biobank. So I don't want to bore you with technical details, but basically we apply a relatively complex multi-stage machine learning spatial temporal models. This model has multiple steps, but the concept is very clear. We use actual observations, which are monitoring data. We link them with a huge amount of potential predictors going from satellite measurements, for example, on land use, or direct measurements, for example, pollution or temperature, and in addition to many other data that you can link, for example, socioeconomic indices, urban features, and many others. And we train this machine learning model to predict them the exposures at very fine level, at the moment 1 kilometer grid, across the whole Great Britain. So what we obtain is a map of these exposures across the whole domain of Great Britain. And here I'm showing the accuracy of the model, which looks already relatively good. So it's a comparison for specific monitoring data, the series, the comparison between the observed and the predicted from the model, showing that the model is relatively good already to predict at this level of resolution. And once you have these very large data, you can link these daily exposure levels to residential addresses of the UK Biobank participants. In order to do that, you can use different methods. In particular, in this first step, we use an interpolation method, making the best use possible of the 1 kilometer grid data, but also creating some linked data that is impossible to backtrace, and therefore preserving the confidentiality. We can repeat this approach every day, and trust me, it's a lot of data to crunch, and therefore to create daily series for each address, and from the exposure history, residential history, of the subject, then reconstruct individual level series. What we get is some preliminary, these are preliminary results of the first linkage, a series of observations at daily level for pretty much all the participants in the UK Biobank. Almost all of them, they have residential addresses, and this data spans from the beginning of last century to 2017. So we have already a data set already developed and sent back to the UK Biobank team. Of course, these are still preliminary results, so we are going through a series of checks. But basically, we have already reconstructed exposure series for PM 2.5, which is particulate matter, specific pollutants, and mean temperature at daily level for each participant in the period 2006-2020. It's a lot of data for our perspective. Of course, if compared to the genetic data, it's not that much, but the final database is almost 92 gigabytes stored in 20 files at the moment, but we have a smaller data set, for example, with annual means for all the subjects, and some preliminary results just on the exposure assessment. These are the distributions of the annual level for all the 500,000 participants in the Biobank across the period 2008-2018, consistently with what we know already from the pollution across Great Britain. We see a decrease in time, but still the levels are well above some guidelines values, for example, from the WHO in 2005, and especially from the last measure, the last revised version of the WHO guidelines of 5 micrograms per cubic meter. So we can easily find some associations already with health outcomes. Of course, the novelty of this is also that we can also derive daily series, and this is an example for 2018 for 3 different subjects, showing how the exposure is completely different, not just between them, but also within them, with spikes at different times of the year, depending on where they live in that moment. Now, final slide, future plans. Of course, we plan to repeat these exercise for other environmental exposures, preliminary, other pollutants, but also potentially pollen, reconstruct historical exposures. At the moment with this modeling, we're going backward only to early 2000, but we are planning also to go backward in time. And we plan to release all the data in the UK Biobank in appropriate format and documentation. Potential extensions are, of course, to model indoor-outdoor concentrations, time activity pattern using mobile technologies that I'm sure the next speaker will be more precise about. So thank you very much.
Thank you. Now I'm going to introduce Professor Aidan Docherty. Now, Aidan Docherty is Associate Professor and Wellcome Trust Senior Research Fellow at the University of Oxford, and his research group develops reproducible methods to analyze wearable sensor data in very large health studies to create a better understanding of the cause and consequences of environmental interactions and personal behavior on human disease. And what we're going to hear is Professor Docherty's presentation, which is going to build on these principles, and it's entitled Wearing Phenotyping in the UK Biobank.
Many thanks, Stephen, and Antonio's talk has actually set me up quite nicely there. So, and in this talk then I'll explain about the wonderful opportunities that we have to use wearable sensors to help transform and redefine how we can measure some key exposures such as physical activity, sleep, but also circadian rhythms, heart rate, etc. as well. So these wearable technologies can continuously and more objectively measure such exposures and really do offer a step change in terms of the measurement compared to what we had before, where we usually relied on self-reported measurements or this kind of small snapshot measurements in an unrealistic or constrained laboratory environments. But unfortunately, the impact of wearables in population health has been disappointing thus far, and that's been mainly due to a reliance on small-scale, descriptive, or at best cross-sectional studies. So what we really need in this space are large-scale, longitudinal studies. And as in so many other areas, the UK Biobank is the genuine world leader in this space. Because in between 2013 and 2015, over 100,000 UK Biobank participants generously agreed to wear a wrist-worn accelerometer on their dominant wrist for 7 days. These devices measure motion or movement in 3 directions, forwards and backwards, side to side and up and down, and do so 100 times per second, meaning that we can get an exquisite measurement of people's physical activity status. And of course, the question is, does that 7-day measurement, does that give us a good measurement of a person's habitual activity for that period in their life? So 3,000 of those participants agreed to take part in a repeated measurement study, whereby they had 4 7-day measurements spaced about 3 months apart a few years later. And if we take the average of those 4 7-day measurements and essentially regress it against their original baseline measurement from a few years earlier, our within-person variation or measurement error lambda coefficient is about 0.7. Meaning that the original measurement, 7-day measurement in 100,000 participants, is really well fit for purpose for epidemiological analysis. And then one can do a number of different analyses. The example here shows accelerometer measured physical activity on the x-axis and its association with incident cardiovascular disease, whereby already in this subset of participants, after 7 years of follow-up, over 4,500 incident CVD events have accrued. And the major take-home message in this is that the strength of the association between activity and cardiovascular disease is much stronger than we had previously thought when relying upon self-reported measurements that are more noisy inherently. And also we're getting much more clarity on the shape of the dose-response association between activity and cardiovascular disease as well. And furthermore, by being embedded within the wonderful UK Biobank resource, we can combine the activity data with genetics, which opens up avenues then around causal inference analysis that is traditionally really difficult with particularly lifestyle and behavioral traits. So there are now a number of publications using the biobank genetics and accelerometry data to show that increased activity reduces one's odds of being diagnosed with colorectal cancer, hypertension, depression, and a range of other outcomes as well. So, but as well as that, because I said we're measuring this human motion 100 times per second, there are many more detailed measurements we can get. Additionally, for example, by using machine learning methods that extract relevant features in the data and take into account the temporal dependencies, we can begin to identify and distinguish between activities such as sitting versus walking versus driving. And a really nice example of this is the paper shown here, whereby we've characterized sleep sedentary behavior, light intensity physical activity behaviors, and moderate intensity physical activity behaviors in the UK Biobank participants. And then have done a compositional data analysis to associate variations in these functional behaviors with incident cardiovascular disease. And I quite like the plot in the bottom left, because most mornings I often toil with whether I should stay in bed for an extra hour or get up and go for a run. So what we've got here in the analysis is we're trading off sleep versus moderate physical activity behaviors while holding the others constant. And the y-axis shows the estimated hazard ratio with respect to incident cardiovascular disease. And we can see very clearly the benefits of engaging in even small amounts of extra moderate intensity exercise. And the machine learning methods that are now being developed, thanks to the collection of this resource, are allowing us to identify new and exciting exposures, such as, for example, sleep architecture. So on the top left of my slide, we've got a typical, the movement trace for a typical night in bed. And what we would really love to characterize from the accelerometry data is whether a person is awake, in deep sleep, such as N1 or N2 sleep, or in lighter sleep then, such as N3 or particularly REM sleep. So in collaboration with colleagues, the RAIN study in Western Australia, we have developed recurrent neural networks to measure sleep stages then as validated against polysomnography in 1,300 individuals. And we've got a kappa score then for the machine learned from just the wrist-worn accelerometer trace of 0.36 versus our gold standard of polysomnography for awake versus REM versus non-REM. While not perfect, this is certainly very far from a random measurement, and we can take into account that uncertainty then when doing population level inference in the biobank data set. So for example, what we can now observe then are very striking differences in REM assessed sleep in biobank participants who report to usually have insomnia symptoms versus those who report to not really have insomnia type symptoms. So this opens up an exciting new set of phenotypes that we will of course return back into the resource for the benefit of the worldwide research community who use the UK Biobank resource. And wearables additionally offer the opportunity to measure physiological status. So Barbara Cassidy at Oxford then leads the enhancement of the UK Biobank resource, whereby cardiac monitors are being given out to a target of 35,000 participants. So these are single lead ECG devices that we're asking participants to wear for 14 days. And they also have onboard accelerometer traces that give us opportunities to improve our measurement of activity and sleep in these participants over the age of 60. And already the preliminary data coming in from this is very promising. So looking at data from the first 12,000 participants, the consent rate is very much in line with the larger collection of wrist-worn accelerometry data in 100,000 participants. Participant compliance, as for so many UK Biobank enhancements, is phenomenal, with a mean wear time of 12 out of a possible 14 days of wear. And also, we've got some good face validity, whereby 1% of women and 3% of men, we believe, have indications of AF from their cardiac monitoring trace, which again is in line with what we would have anticipated at the start. So again, this is a really exciting enhancement to the UK Biobank resource that will, of course, be there and available for the worldwide research community to use over the coming years. So my final slide, I would just like to finish with a call to arms of how we can do even better in the future. So first of all, Naomi talked in the morning about having perhaps a remeasurement of particular exposures, and it would be so powerful if we could remeasure the 100,000 biobank participants with new accelerometry measurements to see changes in activity over a 10-year period how that's associated with future disease risk. Furthermore, I would really love if we could capture data in many more UK biobank participants, because that would allow us to identify a greater range of genetic variables associated with activity and sleep and circadian rhythms that would transform our ability to do causal inference analysis of behavioral traits. And finally, just building upon what Antonio said, what new exposures could we measure in a new assessment of wearables in UK Biobank? Perhaps we could measure PM2.5 in a wrist device. So to finish, I believe there are absolutely wonderful opportunities to use wearables to transform our ability to understand the causes and consequences of disease. Thank you very much.
Thank you very much, Aidan. That was a wonderful description of these wearable technologies, and I'm sure we shall come back to these in the discussion because it adds a whole new dimension to the use of these cohorts like the UK Biobank, and obviously creates a greater level of resolution and granularity for some of the observations, as you clearly pointed out. So finally, and our fourth presentation today is going to be given by Professor Ben Lacey. Ben is an epidemiological and public health physician, and he leads the UK Biobank Epidemiology Group, and he's based at the Clinical Trial Service Unit and the Epidemiological Studies Unit at the University of Oxford. And he's going to build, I think, a bit on what Aidan's been talking about, because he's going to be talking about UK Biobank enhancements in environmental exposures. So thank you very much indeed. Over to you, Ben.
Thank you, Stephen. Yes, so Stephen said I'm Ben Lacey, and I'm an epidemiologist and public health physician with the UK Biobank Epidemiology Group based at the University of Oxford. Yeah, so as Stephen said, I'm going to give an overview of the environmental exposures we have in UK Biobank, the enhancements that we have made over the last few years, and then some of our ideas of how we're going to enhance these exposures for environmental health research. So I think, as the previous speakers have made clear, but it's worth emphasizing, environmental exposures encompass a wide range of external factors that affect health and well-being. And that's not just the substances that we normally call environmental hazards that might affect the air that we breathe, or the food that we eat, or the water that we drink, but also the wider physical environment, including housing quality, occupational risks, or the transport systems that might directly impact health, but also shape the behaviors that have an impact on the risk of infectious and chronic disease, and also our ability to access services. So in terms of the environmental exposure data collected by UK Biobank, there's some information that's particularly relevant to environmental health that was collected at recruitment using the touchscreen questionnaire and the verbal interview. And that includes the current address, country of birth, and if that was in the UK, the region or the city where the participant was born. And then there's also questions related to indoor air pollution, including the fuels that were used for cooking and heating, passive smoking exposure, mobile phone use, and occupational factors, including shift work, physical activity at work, and exposure to noise. And that information was collected again at the first resurvey and at the imaging visits subsequently. And then in addition to that, there's the web-based questionnaire that collected data from a subset of the participants in 2015. And that was a lifelong occupational history with much more detailed information on the type of work, exposure to environmental hazards at work, and any work-related health issues. So address data is particularly valuable to environmental health researchers as it allows them to explore multiple potential environmental risk factors with linkage to UK ecological environmental databases that are often made publicly available. So the full address isn't released to researchers, but the address or postcode that's used to identify the 1 kilometre grid square using the Ordnance Survey National Grid Geographic Reference System that contains the address. And that data has been provided for the address that's been given at recruitment, but also following recruitment, whenever UK Biobank was informed that a participant had moved, that data has then become available to researchers. So this is just a very small selection of the papers that have been produced on environmental exposures in UK Biobank. And as you can see, researchers have made particular use of the address data. So for example, there's been over 50 papers so far looking at air pollution alone, but you can also see some papers on noise pollution, the effect of green space, and the built environment. So that work has been facilitated by the development and incorporation of some key environmental data sets into the resource, such as the data on air and noise pollution that was put together by Anna Hansel and her team at Imperial, and measures of the built environment, such as the UK Biobank Urban Morphometric Platform, developed by John Gallagher and Chinmoy Sarkar, and then measures of green space and coastal proximity from Ben Wheeler at the University of Exeter. And there's also data sets that have been generated more recently as a result of the work that's been done on UK Biobank. And those data sets are then returned to the study and they can be used by other researchers. And I've just listed a small sample of those here, including on air temperature, air pollution, natural spaces, and hours of sunlight. So where do we go from here? Well, UK Biobank held a workshop at the end of last year on the social and environmental determinants of health. And there were 3 key areas that emerged. The first was to define the current and past residential history of participants. So that included and that's the addresses since recruitment. And as you can see from the heat maps here, there's been a lot of movement over that period. So those areas that are quite defined red areas at recruitment have now become more dispersed over time. But also, if possible, to try and get residential address from before recruitment. And that's certainly something we're looking into in UK Biobank. The second area of interest, as Aidan went into, was the use of wearable devices. And this stems from the fact that, except during the COVID era, people are not generally confined to their homes, and that more granular data is needed to understand where people are spending their time and their movement through the environment. So this includes whether we can use the existing data that we've collected from wearables to understand the validity of that address data, but also whether or not there is additional data that we can collect from wearables or from apps, perhaps downloadable onto participants' mobile phones or other devices that provide more granular location data. And there's lots of examples of how this might work, and I've just illustrated one study here from the University of Manchester called Cloudy with a Chance of Pain, that looked at the environmental determinants of long-term pain conditions in 13,000 participants using a smartphone app to both monitor the symptoms, but also to collect GPS location data that could then be linked to local weather data. And the last area of action was on linkages. So we're aware that there are very different types of exposure in UK Biobank, but environmental exposures in particular need linkage to other data sets. So I just wanted to emphasize to the environmental health community that UK Biobank is very keen to support work that increases the range of linkages that would improve the spatial or temporal resolution of those and the time periods for which they're available to maximize the value of data for environmental health research. And I just wanted to acknowledge the wider UK Biobank team, our funders, and of course our 500,000 participants.
Thank you very much, Ben. And obviously these resources are absolutely amazing, considering the level of importance, really, of these environmental exposures that are beginning to come to light now. I mean, what's very intriguing to me is the magnitude of these effects that you're beginning to pull out of these extraordinary linkage studies. So before I go into some of the panel's questions, I wonder if, first of all, I could ask all of you really to give some consideration to early life origins of these chronic diseases we've been talking about today. I mean, are there any really powerful data sets that enable you to be able to make these sort of observations in children as they sort of turn into adults and progress? Because it strikes me that that all of you in a way are pointing to early life as being an important part of the evolution of these chronic diseases, but the ability to actually resolve that with certainty is not clear yet. I don't know whether anybody wishes to have a go at that one.
Well, Stephen, probably I can start giving my comments. Well, in the context of the UK Biobank, of course, it's something which poses more difficulties compared to other cohorts, because, of course, it's a cohort of adults, meaning you need to reconstruct exposures far back in time in order to understand the potential risks in that specific windows. It's certainly possible, but of course it poses more complexities compared to a birth cohort, for example. And I know for sure there are current endeavors with other cohorts, in particular with the birth cohorts, to assign exposures at different periods during pregnancy or early life to disentangle potential windows of susceptibility.
Yeah. I mean, Dale, in the US, do they have large cohorts of children and longitudinal studies, a bit like the UK Biobank?
Yeah, so there are some smaller cohorts, for looking at children and following them forward, but you have to be a lot younger to be able to start now and keep going forward. I think there's a tremendous amount of interest that we have at our institute in the role of early life exposures, and the challenge for us is how good are the exposure data going back in time. Monitoring standards have changed for something like air pollution, and you can go back to maybe 1960, but through modeling, but you can't go back further than that. We've been trying to reconstruct residential histories back to childhood, and I think we're going to have more success with measures of socioeconomic stressors, because we have census data where we can construct indices of exposure going back to childhood, which is something we've started doing in our breast cancer cohort.
Wonderful, thank you very much. Well, let me go to some of the questions that people have put into the chat box. The first is for you, Dale, if you could try and deal with this one, which is related to the particulates, PM10 and PM2.5, and the breast cancer you mentioned. The person has asked why that is not related to lung disease, which of course it is. But I think probably behind this question is something around underlying mechanisms as to how and why particles have picked off this particular organ to manifest as a risk factor for cancer.
Yeah, so it's actually surprising that we can measure chemicals related to air pollution in breast milk, in breast fluids, and in breast tissue. So we know that tissues throughout the body, including the breast, are being exposed, and a wide range of mechanisms have been proposed. The effects that we see are quite small, and relative to things like cardiovascular disease and lung disease, which are much more obvious targets for chemicals that you would breathe.
Yeah, excellent. Thank you very much. And of course, it's a very hot area of interest. There's quite a bit of interest beginning to well about lung cancer and air pollution at the present time. Have you got any data on that at all or not? This is the non-smoking lung cancer.
Are you asking me?
Yeah.
In our cohorts, it's actually, our cohort is smaller than the UK Biobank, and so in a cohort of 50,000 women, lung cancer is a little bit less popular.
Yeah.
So it's less common than breast cancer in a cohort that's been enriched for breast cancer. But there are cohorts in the United States that are particularly addressing these questions.
Yeah, thank you very much. Okay, well, let me move to Antonio, if I may. And we have a question here, Antonio, about other sorts of environmental impacts, particularly the effect of heat waves on the population and related environmental dramatic insults. Have you been able to pick up anything in your cohort work on the UK Biobank in that area?
Well, not yet, because we have just linked the data, so we are still analyzing the data, but surely is an interesting area of research. As I mentioned it very briefly in my presentation, there are a lot of studies on temperature and health, in particular mortality, but many other outcomes. But most of them are mostly carried out at using administrative level data and aggregated level. So there are much less if compared to pollution on individual level analysis, and therefore we know much less about individual factors that can enhance or increase the risk or maybe the resilience of specific individuals. So for sure, this is a very interesting area of research, and this was one of the main reasons for trying to link daily data to the UK Biobank, although it's a very big endeavor, because it allows us to study effects of specific days, for example, in conjunction with some heat waves that we have experienced very, very recently also.
Yeah, indeed. And I think all of you have made reference in your talks to interactions between different environmental exposures in feeding into clinical and disease phenotypes. I mean, is this a new technology now that's emerging? I mean, you mentioned machine learning as an example of being able to deal with the complexity of these interactions, but I don't know whether any of you'd like to just come in and tell us a little bit more about environment by environment interactions as opposed to gene by environment interactions.
Are you still asking me?
Anyone who can answer the question, yes.
We have a recent example where we were interested in exposure to light at night in relation to breast cancer risk. It's a sort of a topic of intense interest in the United States. And we saw some sort of very subtle associations between light and night and breast cancer. And then when we adjusted for other exposures that you can imagine are highly correlated with light at night, including urbanicity and noise and air pollution, the effects totally disappeared. They went away. So it really is important to consider the correlation between all of these exposures that we're interested in.
Yeah. And I suppose in terms of a policy development, because a lot of this work that you're doing, will eventually feed into policy, no doubt, and hopefully behavioral changes, whether individual, population-based or government-based. And so these data sets that you're all working with, do you have a mechanism of sort of getting this information across the divide so that policy workers can actually start using it to reshape policies, either at the local or the central levels?
Let's go first there, Stephen.
Go ahead, Ben.
Yeah, please do.
Well, I was just going to make the point that I think the kind of starting point is robust evidence. And, talking to Antonio and other environmental researchers, I think one of the strengths of UK Biobank is the individual level data and really the depth of data that's available. And I know Dale has made this point before and in her kind of previous work about the importance of accounting for the social determinants of health when you look at environmental determinants of health as well. So I'd just say to any kind of budding environmental researchers out there that that there are real strengths, I think, for using the UK Biobank, and it's going to get stronger over the next few years.
Yeah, indeed. So yeah, well, it is an important part of this whole debate of using epidemiology in a way that sort of helps shape how we move forward in obviously preventing these terrible human diseases that we're having to deal with. Let me go to Aidan, if I could. The idea of these wearables, obviously, you've given some examples, some nice examples, and you just touched on the end of a sort of widening of examples of using wearables and apps and other ways of recording personal interactions. I wonder whether you could just expand a little bit more on that. I mean, obviously heart rate and sleep quality, and these are things that you can measure at the present time to some degree, but are there some exciting new developments in the personal monitoring of individual responses?
So there are really exciting developments in industry, and the likes of Fitbit, Apple, etc. They're just going to continue innovating regardless of what we do. And we'd very much like to piggyback on top of that to include in, for example, future enhancements, perhaps of the UK Biobank and other cohorts. And for that, I guess that requires, or will require collaboration and with industry then to understand, because there are lots of publications on kind of sensors that seem to have some hope, but then what can we, what's out there that's robust, that we know we can feasibly measure in hundreds of thousands of participants, and that begins to narrow down the pool of new measurements quite a lot. But I think a key thing we need is that such measurement technologies are passive in their nature. So a participant puts it on, forgets about it, and then it's up to our job as researchers then to try and come up with clever methods to infer measurements from that. But I think the minute we start asking participants to actively do measurements, we begin then to get quite serious selection biases, etc., which we definitely want to avoid.
Yeah, well, that's really exciting. In fact, the person who asked the question really pointed to Apple, which is just one of these large companies advertising about their research collaboration using wearable data, and how good, universities, maybe higher education institutes across the world are actually going to those sorts of companies and making the kind of, I don't know, the linkages, I suppose, to use the term broadly, to these companies. I mean, is there a real effort to try and bring this in?
There are currently efforts kind of working, I guess, a little bit silently in the background. And last year, the British Heart Foundation then sort of convened a workshop then with sort of key players in industry, along with the sort of the major UK cohorts, and to see what opportunities that there might be. There are a lot of considerations taken into account, and so one of the key ones is an individual's willingness to wear, share, and care. So will they wear a device, and might they share information from it, and care enough to wear it for long enough? So it's so we've got to consider all those selection biases, and we probably would prefer a model whereby rather than a bring your own device, it's more so pushing a device from the cohort out to the participant, just again to try and get as great a diversity of participants as we possibly can. Fantastic.
Thank you very much. Maybe I could go to you, Ben, with this, because it's about the UK Biobank and real-time or near real-time analysis on lifestyle behaviours. Obviously, you touched on some that you're doing. I mean, are there a particular range of lifestyle behaviors that are also geocoded, linked to geocoded data in the biobank that go beyond some of the things you've been talking about?
Well, this might be one for Aidan, actually. I mean, I know that he's done some work on whether you can take wearables and infer from that, especially if you combine it with other data that's collected within UK Biobank to tell us what activities a participant happens to be doing. There's no doubt that that's extremely valuable. I mean, you can get self-reported measures that an individual jogs or cycles to work, but if that's then replicated in the accelerometer data, you know that you've kind of you've got a really good measure there. Yeah, there's no question that where it's possible to collect objective data, be it through wearables or other devices, that's obviously extremely valuable.
Sure, absolutely. Yeah. And one of the questions that's also come up is how one interfaces data that's been collected on environmental exposures and environmental measures with health-related data when they haven't been collected specifically for that particular purpose. The sort of interfacing here of these different, often massive data sets. I mean, is there a special sort of technology that enables data sets that have been collected for different purposes to be interfaced?
It's up to me, Stephen.
Well, I think anybody. I mean, I'll just use the Met Office, for example, who collects a lot of data on atmospheric pollution as well as temperature and all sorts of other things, and connecting those data across the whole country with health data. I mean, how easy is that to do, to get sort of further national representation of these interesting areas that you're expanding upon today?
Well, I was just going to say that I think in terms of the kind of technical aspect of collecting the data and making it available, I think the research analysis platform that we've got now in place in UK Biobank will really help that.
Yeah.
In terms of the analysis, I wonder whether Antonio has something to say with regard to that.
Well, it's definitely possible, meaning we are already performing some analysis at small area level across the whole country, and it poses more statistical problems than problems in collecting the data. For the UK Biobank, as I mentioned, there are this additional complexity of reconstructing individual series. But once you have done it, it's definitely possible to generate highly informative exposure histories for a set of different environmental stressors, and therefore this puts you in a completely different perspective in terms of the kind of analysis you can do. Actually, it's a novel area if you want a research in which you can link very rich data from an environmental point of view.
And just as we start to get towards the end, I mean, Dale, it did seem to me in those big cohorts you were talking about with these environmental and occupational exposures, that's exactly what you've done, is bring these data sets together. I don't know whether you have any comment to say on that.
But we've done this in a potentially simplified way compared to the future. So collecting the massive amounts of data that you can get from wearables or downloading daily air pollution data and trying to make summary measures out of that you can link to some future health events. It's going to require really new statistical models. And, for some of us who have started out using questionnaire data, it's a big leap. So I'm glad that there are people like some of our panelists who are venturing into that area and breaking new ground.
Yeah, good. Thank you very much. Well, I think our time is now up, and I just want to thank you all very much indeed for wonderful presentations and for kind of creating such an incredible forum to have important discussions about how we utilize these data further going into the future. It's been a wonderful session. I think we're all impressed. I think that the environment now is coming to the forefront as a serious driver of many of the diseases that fill up our hospitals and our clinics. And I think the more we have of this work, connecting our environment and what we do in our environment to these adverse human health outcomes, the better. And I just want to thank you all very much indeed for your brilliant presentations and for handling the questions so well and so adeptly. It was absolutely superb. And so on that, I'm going to sign off now and say thank you all for listening. And I think there's a tea break coming, but maybe we have somebody just going to say something first. So please.